we have had a Model 3 battery project going on around here some time, but it hadn't been too serious. And the reason is we've had a lot of work involving producing the PowerSafe 15, a dozen of those. We're doing 8 or 10 of our Tesla battery module control units a week now. And so everybody's been busy fabricating stuff. Of course, we had the PowerSafe 100, the PowerSafe 60, and then the 15, which is for marine and RV. Wayne Reavers, by the way, loves his so much he wants me to turn it into a 30 and a 48 volt. I tried to tell him that you can't do that. A design's kind of a design, guys. It's not a design, but all different. and things feed into each other. Anyway, we've been very busy, but I have several Model 3 modules laying here. And Colin and I have been working on a prototype board to talk to it. As it turns out, the chips on the battery management system for the Model 3 modules are not repurposed LTC chips. In fact, both of them are ASIC chips, or application-specific integrated circuits designed for Tesla, which is what they said. Well, they weren't kidding. They're very specific and have some very interesting properties. They transmit in both directions in a loop and at 2 different frequencies. And there's 2 sets of chips, and they're entirely redundant, very different BMS systems. And so there's 2 BMS systems on every module, and kind of some, it's like the isolated serial peripheral interface, SPI, ISO SPI that LTC did, and it's nothing like it. So we've never seen anything like it. We had to upgrade our test equipment to even be able to figure out what it was actually doing. Just some 100 megahertz scopes with a lot of storage and so forth. We designed a board, got it back. It did not work. Colin kind of hand wired it into a little bit of a rat's nest and got it to sort of kind of work. And so he did a redesign on the board, and I sent that off 10 days ago. But it's Chinese New Year, so we'll get that back sometime in February. The Chinese have what they call 996 now, and the whole country is working 9 in the morning till 9 at night, 6 days a week. And then they all go on vacation for a month. And they go on vacation on all their holidays, and they go on vacation on all our holidays too now. So whenever I'm trying to do something with them, some holiday or another gets right in the middle of it. But God love them, they're working 12 hours a day, 6 days a week, when they're not on holiday, so I don't quite blame them. Anyway, the other aspect we have is a full Model 3 battery pack. And this week, things have kind of slowed down over the holidays, and so I started to attack the Model 3 flat battery pack. And, I got some connector diagrams and some wiring diagrams, and was just kind of going over them. And we've got 4 people now here. Dan, who's our lead tech, Zeke, and then we have 2 interns, Ryan Shaw and Brandon Dury.
There we go.
And so we've got a whole team, and they were kind of curious what I was puttering around with over here. And I stopped and thought about it, and I said, I've done this 3,000 times. Why don't you guys just do it? My favorite TV show is House, and he's got a team of 5 or 6 doctors, and he poses a question to them, and they all shout different solutions, and he berates them with a great deal of sarcasm, as is the resident smartass, which I always thought, I'm kind of like that. I can say smartass things and tell you don't know what you're doing and do it over again. And so we'll just do this like House. You guys go figure it out. The process has actually worked pretty good. And the key is this car, if you'll recall, we took the front end off of this car and put it on the other one because it was wrecked in the front. And this one's wrecked in the back. And this panel here, which includes the charge port, is actually kind of difficult to replace. I watched some guys do it on YouTube. They had to cut it out and weld new stuff in, and it was one of those sped up videos, and it still went 20 minutes long. Just showing them running back and forth doing this, and by the time they got done, I didn't want any part of it. So this was probably the better car. I think it only had 746 miles on it.
Yep.
But it was a more severe wreck for our purposes. The other one was wrecked on the front, and the front end of the Tesla Model 3, kind of everything is just sort of bolted on there. And so we took the pieces off the front of this, including the hood, the bumper, the radiator, the, what do you call it, the crash impact
Crash
stuff, headlights and everything, and one of the doors, maybe 2 of the doors, and put it on the other car, and it's now driving. Richard's going to do a session on how you get one of those titled and licensed as soon as he figures out how to do that. Leaving this car, but it's still intact, and if you connect a 12-volt battery, it comes alive. Obviously, it has a few error messages. But the important part is that the contactor's closed and the battery empowers the car. Now you have power for your 12 volts, and you have high voltage power when those contactors close. That's our mission with the full battery pack. So here's one that does what we want that one on the bench to do. I'll figure out how it's doing it on the car, and we'll go do it there. So what did you come up with, Danu?
So what we have here, quality test is checking. This is the gray connector that connects into the full pack on the
What
Model
is that,
3.
X098?
Yeah,
I think.
098.
Yes.
Right.
That's
Yeah,
it.
that's the connector.
And this ties in inside the car. I believe it goes to the vehicle control units. So what we were trying to do is figure out what it needs to wake the battery up. So we found out that it has exactly 13 wires, and what I did was simply wire this connector from the silver car
From the wreck out front.
rack out front. So I cut it, I spliced them open, and I put it on a breadboard, and I simply used some jumper cables to go from the breadboard to the actual gray connector in the car.
Now this connector is the control connector to the battery. Everything else to the battery is high voltage, to the front and rear drive, to the air conditioning and heating system. There's some coolant connections, but all the electrical interface or intelligent interface to the battery is through this connector.
Yep.
So that let you put that between the actual car connector and the battery.
Yes, sir.
And then what do you do with that information?
So what we were trying to figure out is what we need to wake the battery up. So we tried taking one wire off at a time from the 13 wires to see how many we really need for the contactors to close. So once I got these all connected, I switched on the car and I heard the contactors close. And so what I did was I next removed 2 wires, which was I started with the charge port can. I removed it and then I gave it 12 volts and I heard the contactors click again. So that proved that we didn't need charge port can for the contactors to close on the full pack.
So you disconnect some wires,
Yep.
apply the 12 volts, and you can audibly hear the contactors closing. It's a pretty loud deal. Hold on. Okay.
And then, so it came down to we only needed 7 wires to really close the contactors, because when I removed the 7th wire in there and gave 12 volts, it didn't close the contactors. So so that way I found out that we needed exactly 7 wires to close. And 2 of those wires were the HVIR loop, high voltage interlock loop, and 2 wires were the powertrain can. And there were 2 wires of 12 volts and 1 wire of ground.
Okay. So if you had those hooked up, you could make the contactors close.
Yes.
All right. The high voltage interlock loop, Tesla doesn't like to have high voltage loose in the car unless everything's already hooked up. And so it runs out those 2 pins. It's just a loop through the rear drive unit, the heater or air conditioner unit, and the front drive unit if you have one, and back to the other pins 1 and 3. There's a 60 ohm resistor in the Kat, does that test apparatus meet with your quality assurance approval? She's got to get in there for video now. So as it turns out, the battery is kind of stupid. It doesn't care if you have one or both drive units hooked up. It needs about 60 ohms to detect that that loop is closed. It'll do it at 120 as well.
Yep.
So sort of anything in between there would be appropriate. So you had 2 wires that were 12 volt and 1 that's ground. There's no magic in that, right?
No. So.
It's just 12 volts DC
Yep.
and ground. Oh, there was another thing that you found. Something else that had to be hooked up to the battery.
Yes, when we tried it on the bench, we weren't getting it to come on, and we were thinking about what that could be, and then we found out that car was actually giving 12 volts into the PCS, the power conversion system.
There is a power conversion system inside the battery. Well, that's what they call it. It's the charger for the battery. But it also converts high voltage DC to 12 volts DC, really about 15 volts DC.
Yeah.
And so you have to apply 12 volts from the battery to that, or it's not going to switch on.
Yep. We tried removing
Anybody know why? I don't either.
Yeah.
Anyway, you have to have, there's 2 terminals, and the connector for this and both terminals are under the rear passenger seat on the passenger side. And so you have to have those 2 PCS terminals hooked up too.
Yep.
But you only need 7 wires to the control connector.
X098.
And we have, of course, our system, the OBD2 adapter, that we can plug in to the powertrain can behind the console. And in fact, we have a version of that doesn't really do OBD2. It's just a CAN monitor version that has the connectors to connect in there. for analysis and monitoring with Collins' excellent SavvyCAN program. SavvyCAN is like a poor man's version of Vector's Canoe, which is a software suite that starts at $10,000 because it was originally written for about 17 guys worldwide. But now CAN is kind of popular. And anyway, Colin did a totally free open source version of Vector's suite. I actually like Colin's better. To capture CAN, play back CAN, and so forth. And Daniel wouldn't really trust all that. He wanted to capture it at the breadboard at the actual place that it went in the battery. As it turns out, there's no difference. The console connection would have done just fine. It's called the powertrain CAN, really, but a lot of people refer to it as the vehicle CAN, as opposed to 3 or 4 other CAN buses in the car for entertainment and windows and that sort of thing. So we did a CAN capture.
Yep.
And we did a playback, and it didn't work. So we had to work on our playback speed and go back and look at our logs and calculate how often, at what rate these frames were thrown at, and adjust SavvyCAN, which has controls for that, to send it at the right rate. So we put a resistor across the HVIL, fed in the CAN,
Yep.
and got it to close the contactors without really anything from the car. And we did all this on the car.
Yeah. It took a couple tries.
Well, yeah, there's this is the problem with the reverse engineering, and as I was describing to them, it's not quite the genius event that everybody thinks. There's 2 schools of thought, Nikola Tesla's and Thomas Edison's. I'm in the Edison camp. It's 1% inspiration and 99% perspiration. And so it looks like genius. It's sort of tedious. And one of the things I was trying to get these guys to is how real that is. It's not a native talent. It's grunt work. And you just do it by iteration. Unfortunately, it's not very forgiving. If you have the right CAN, but you don't have the HVIL loop connected correctly, it doesn't work. If you have the HVIL loop and the CAN connected correctly, but you don't have the 12 volts to the PCS terminals, it doesn't work. If you have the CAN right and the HVIL loop right and the PCS terminals, that doesn't work unless you have both terminals of the 12 volt connected.
Yep.
Now, it's already getting 12 volts in one terminal. I know it should work. But the guys that designed it, they just did it that way. Did they do it for a good reason? What the hell difference does it make? They did it. And so you can be 4/5 of the way there, and you've got nothing. And this is why most people fail in reverse engineering. If you do 127 tests and it takes 128, if you quit after 127, you might as well not have showed up.
Sure.
It's kind of brute force quantity stuff. You have to think it through. That's true. It's like a puzzle. But you have to have all the parts. Having most of them right is not encouraging. You don't get any feedback that says, you guys are almost there. by golly, I think you've almost got it. No, you either don't have it or you have it. And so you can work at it for 19 consecutive days. And if it takes 20, you didn't get there, and you quit a loser, and you went home and said, well, it's just too hard. I don't like to lose. So if it takes 20 days, I might spend 60 on it. Just to do it 3 times.
Yep.
It's persistence is the admirable value here. Genius isn't. There's only 13 wires here. Some combination of signals on some number of those wires will close that contactor, I guarantee you. But it can be quite a thing. For example, you could have something going out the charge port can and a timed response required, to get there. Daniel kind of cunningly eliminated that possibility by unplugging the wires. And it still closed the contactor, so we don't need to worry about that at all. And so it's a process of logical, step-by-step troubleshooting to eliminate the unnecessary and determine the required. And did you all find that a educational process?
Yes. Very much.
So the team, the 4 guys, did all this. I occasionally made a smart-ass comment like Gregory House does. When they would get discouraged, I might suggest something, and but I didn't do it. I've done it a lot. I believe it's valuable, and I would do it again, but I'm old and my knees don't work very good. Here's 4 guys, and let them do it, and it'll be educational for them. Less so for me at this point. Once you've done 30 of them, well, you learn something every time, that's true. But it was more valuable for them than it would be for me. And so that's where we went with it. And then we have to translate that to the battery on the bench. And let's go take a look at that. Here we are at the battery pack on the bench, a full Model 3 battery. Danu, tell us what we got set up here.
Yes, so we have the connector that we have wired in with a CAN going into our ESP32 microcontroller, and then we also have a HVIL loop with a 100 ohm resistor, and we have 12 volts and ground supplied with a little lithium-ion battery here that is 12 volt battery.
Okay.
And we also have this little thicker wire going into our PCS wired also from this 12 volt battery, and we just put a switch in there so we can toggle it on and off.
So we have 12 volts on 2 pins, ground on 1.
Yep.
The HVIL loop has a resistor on it.
Yep.
And we have ESP32 RET loaded up here. Let's see if we can turn on the contactors.
We have 12 volts off.
Well, we might want to have it on. This is something we haven't got worked out yet. Where do you get 12 volts for this? And there goes our contactors. And you have a voltmeter behind you, wired into the output. What's that reading?
357.71 volts DC.
Success. And so we're turning on the contactors. We'll go into SavvyCAN and put it on pause and quit sending that message, and there we are. And our voltage goes off and the contactor's open. Let's take a look at this SavvyCAN program and see what we did. Okay, here we are with SavvyCAN. We have a connection to our Jevret generalized vehicle reverse engineering tool on our ESP32 board, and we're on CAN 0 at 500,000 bits per second. And I've loaded our capture file here, and it has all the IDs that we captured from the car. And we're going to select a loop sequence so it sends it over and over again. And I have it at a playback speed of 1 and a burst rate of 2, and that seems to do pretty good. And I'm going to load a filter that I call bat filter. And what this is it turns off all the messages that we know that the battery puts out. So we're not going to send messages that the battery is sending anyway. And here is our thing we're receiving, and these are all the messages that the battery is sending. We've turned on 12 volts and we're receiving CAN from the battery, and I've eliminated with the filter all those from our playback sequence. And so we're going to turn on, and there we hear the contactors closing, and they remain closed. And so we're sending all of the captured CAN that we did during a contact closure on the car, and sure enough, on our battery, it is closing the contactors. Now with the blue checks, these are all the messages we're sending. It's doubtful that all of them are needed to do the thing, so we're going to turn them off by unchecking them. And this actually takes them out of the loop real time while we're sending this loop. And we go 5,699 frames, and we loop right back around and send them again. And as long as we do that, and there I paused it and you heard the contactors go off. If I restart it, they come back on and close. So I'm gradually eliminating messages out of this loop, and I'm going to keep doing that until we find a message that causes the contactors to close. If I turn one message off, or maybe more, then we're not going to close the contactors after all. And we've turned off quite a few. They're still closed. I'm just going to keep going here, turning off messages until I get to one that is required to keep the contactors closed. Now, some of them you might have to start, but you don't have to keep. And so we're going to have to play with this a little bit, but we'll see what happens here. And I'm still turning off messages, and our contactors are still closed. And here we go. We're turning off a lot of messages and not losing our contactors at all. So I'm just going through here. Every time I remove a blue check mark, it quits sending that message. In this pane over here, you can see the messages coming in, and I'll turn on auto scrolling so you can see them coming in at the bottom. And these are all the messages it's receiving. But as you can see, we're not getting a whole lot of the ones I've turned off. I'm back here. I'm still turning off messages. If I clear frames, you'll see that that's what we're getting in. So I'm still turning them off here. We're down to 321, 319. Contactors are still closed. We're doing all right. Down to 2C3. And we're turning off messages. And the contactors are staying closed. So there's a whole bunch we don't need at least to hold them closed. $28, $27, $25, $21. Oops, our contactors just opened. And so I'm going to put that one back in. Nothing. We're going to pause it and resume it. And there it is. 221 is the one. That's got it closed. If I turn it off, it opens. If I turn it back on, it closes. How about the rest of these? I'm turning off messages. And that's it. The only message we have turned on right now that we're sending is 221. Oh, I skipped 54F. Nope, that doesn't have any impact. We're down to message number 221. And if I turn that off, they go off. And if I turn it back on, it comes back on. And so guess what? Out of all the CAN on that powertrain bus, the only message we need is message ID 221 hex to turn on and off the contactor. That's amazing. We need one CAN message, and if you don't have it, it doesn't work. If you do have it, it does work. And so there we go. 221. And that's the only CAN message we need, apparently, to run that contactor. If I put it on pause, they come open. You can hear them. And so there you go. We've used SavvyCAN to isolate a single CAN message off the powertrain bus 221 that turns on and off the contactors. Okay, guys, good work. We've got the battery closing and opening with SavvyCAN. I'm going to bring up a little program I wrote to send that same 221 message on the CAN to the battery and see how that works. Let's take a look at that. Okay, I've written a little program to send that message ID 221 to the battery through that X098 connector. But it also gets the CAN from the battery. And both our car and this battery we have sitting here still put out message ID 401. 401 is actually a sequenced series of messages that contain the voltages of all the cells in the battery. Now that's gone away with a software update on the Model 3, and it no longer sends it, as far as I know. There's a possibility that some other can suppresses it. I'm hopeful, but we'll see. We're going to have to try some different batteries. This program, as you can see, EVTV Tesla Model 3 battery monitor, version ESP32-2.010. It's actually a fork of our V2 software at the 2.01 version. So that's why I numbered it that. Here's our run time, our date and time that we got from the National Institute of Science and Technology over the internet. And here's all our cells, 96 cells, of course, at about 3.7 volts each. The first line under that, we simply sum all those voltages for 357.783 volts, and then we average them to get 3.727 on average. Reported voltage is actually a separate CAN message that we'll always get. The sum voltage in these won't appear unless a message 401 is received. The way I've got the software is it simply doesn't print any of this until it gets a message 401. But reported voltage and current we'll always get on another CAN message, and our power. We have no current right now because the contactors are off. Also, from the battery CAN, we find out that our Model 3 battery has a 76.9 kilowatt hour capacity. It has 34.6 kilowatt hours remaining on the battery, and its state of charge right now is 45%. All these are reported values from the battery. They really don't work out perfectly mathematically, but that's what the battery is reporting by Tesla and their battery. It also gives me the lifetime charge and discharge of the car, which is about 1,500% discharges is all this battery has on it. Battery contactors off. Again, this is a CAN message from the battery that reports the contactor state. And here is the battery serial number, TG1182560000KYE. And at the bottom I have that I'm connected to the local access point EVTV as this IP and this signal strength. And that's important when talking to our display or some other wireless functions that we have in the program. I've set it up where I can enter a C for contactors, and I will do that now. And I can hear the contactors on, but there's a second before the battery contactors energize comes on, and that's again, it's not what I commanded, it's what it reported. So I've got a complete loop there. I send the 221 message, and it notifies me by CAN when the contactors are closed. Of course, I can hear them. If we go to debug, I can see our sent and received CAN messages. I'm just going to disconnect here to stop it. And here you can see our sent messages, 221. Boy, I'm sending them a lot. And they alternate between a couple values, and that seems to work fine. And so we also send out some CAN messages for an EVTV display and some other things. But you can see message ID 221 is being sent. Turn debug off. I get my screen back. So back to our screen, we can see the battery contactors are energized as reported by the battery via CAN message. And I can hit my C again and turn that off, and we can hear the contactors disengage, and it reports battery contactors off. And so our 221 message works, and our ability to decode CAN messages from the battery is pretty successful too, and particularly so if we do get that message ID 401. So that's my little program that we created to send the 221 CAN messages and read some of the CAN messages from the battery. And as you can see, I can press C and tells me we're energized. We hear the contactors very clearly. And what do we have on the scope there?
357.71.
357.71. I've got 357.77 and 357.47. Close enough for government work. And so we have taken a battery that mostly just lays there and set it with some software where we can programmatically turn on and disconnect the contactors, and so the output. And given that control, we can now hook it up to an inverter and make power, or a charger and charge, or with an inverter and some micro inverters with rooftop solar, we can charge back in there. So I kind of had to write the software. I don't have them actually coding a lot in C++ yet, but the overwhelming amount of the work, this is the team that did it. And how did you guys like the process of doing that kind of without me?
It was learning. It took a bit of learning, but it was fun.
A little frustrating?
A little bit.
Uh-huh.
The first couple of tries we saw nothing, so it was a little sad. But then once we noticed where the variables were, so we started punching at it, and when we got through.
You know, the part that always gets me is after I get it to work, and then I can't get it to work again. And we had some of that. And what gets you, Dano? Over and over and over.
Yep. Keep trying.
No, what stops you? What causes these failures?
One thing not being right. One connector.
Connectors. We had a bad connection to the battery. It wasn't screwed down tight.
Yep.
We've had every wire in the place almost making electrical contact.
Almost.
And this is aside from the problem of reverse engineering it. You have to fight yourself. Electricity is very unforgiving.
Yep.
That you kind of have it stuck in at the connector, in the direction of the connector, and even close to the connector doesn't mean you have an electrical connection. And we found out over and over again that it wasn't really the battery fighting us, but us fighting us. And that is, it does complicate the thing. You think that you have an indication that this is not working, when in fact the wires aren't actually connected. And that can slow you down and throw off your test results, and you're halfway through it and you realize that what you thought you knew, you didn't actually know. So, but that is the process. I'd love to make it much more scientific, precision, and easy. And then what it is. This is how you do it. This is how the pros do it. This is how the very best do it. By the way, with a PhD in EE engineering and 7 helpers, if you don't screw the wire down, it's still not screwed down. If you don't have an electrical connection, you still don't have one. Yep. And a pin that's on a connector that's in the socket but not really making contact, still isn't making contact. And so that's kind of the process. As annoying as it can be, that's kind of what we do for a living. You guys have been doing some great fabrication and testing, actually, of our production products going out. But hopefully this gave you some insight into the upfront work in the development of a product. Do we have a product here?
I think so.
Not at all. We've got a pile of mess that we can't even rely on to work the next time I press C.
It's a work in progress.
It's not even a prototype. So let's build a prototype box as if we were doing it on purpose to perform this act.
All right.
And let's see how that goes. Stay with us. We're back with our Model 3 full battery pack under examination, and we've made a little bit of progress. Danu and Zeke have been busy in the fab. What'd you guys build me?
We have a prototype controller for the Model 3 full pack.
You know, it looks a lot like the controller for the Tesla Model S battery modules.
Yes, sir. It's a V2 controller basically, and we swapped out some parts and got it to work with getting it to work with the Model 3 full pack.
Do you have the other cable assembly that we didn't use to show them? This is one half of the cable assembly that goes to the front drive unit.
Yep.
We don't have a front drive unit. We don't have any drive units. We just have the battery. So we chopped that in two and put terminals on the other end. That's a 50 millimeter squared cable, kind of like a 1/0, but it's sort of special. It's made of aluminum and has a shield on it, as I recall, and a very unusual connector in the end. Those are probably going to become hard to come by. So you made me a V2 Tesla Model S controller, but on the input used half of
The Model 3 front drive unit cable.
very good. And here we have the output wired up to our 5-digit meter, and the PCS terminals are wired up to that meter. We have 2 wires from the controller to that, and our 12-volt battery over here is wired up to that, and we only have to have that to get started, and I haven't really figured a way around all that yet. Well, it looks great. You've got the same connectors, USB,
Yep.
RJ45 for the 2 cans, our 12-volt.
Yep.
We have the charge enable and the heat enable outputs. And we're using essentially the same controller and shield
Yes, sir.
to run all that. This is, in pretty much, a Tesla Model S battery module controller, but with a different connector. Instead of connecting to the Model S module daisy chain, it's connecting to our control input on the Model 3 battery. In a feat of software legerdemain that may never be since paralleled, I managed to take our Model 3 battery code and kind of inject it into the full code for the Tesla Model S battery module controller. What does this do? Well, it's a year's worth of code that sends data to our display unit over Wi-Fi, wireless UDP, user data carrying protocol, just like our PowerSafe 100 or any of the things that we use with the Tesla Model S battery controller, over-the-air updates, configuration from the display unit, everything we do with the Model S controller, we have retained, and I've kind of just replaced the values. I mean, a battery is a battery, right? The voltage and the high cell, low cell, average cell, current, power, it's all kind of the same stuff. So I've gone in and added a little software module to be a battery in place of our BMS module for the Model S, and have most of it working now, including our pre-charge. We've got our 2 contactors in there. This is like a Model S battery module controller, except we're reading and reacting to the Model 3 batteries. And so I can tell you the software's a mess, but it's functional right now, and most of the cleanup will be taking things out we just no longer need, that nobody will ever see, really. And so that's kind of the state of the situation at the moment. Here's our screen. We're displaying our individual voltages. Now that's kind of a function of this battery. Tesla has updated the software in their cars and eliminated a CAN message ID 401 that provides all that data. But our car over here and this battery apparently didn't get the word, because it's still putting out 401. There is another possibility in that something in the, and this is how I would do it, but I don't know that it happens this way, but something in the MCU of the car is suppressing that output. And that is that unless you toggle something off, it simply doesn't send it. But if you do, it would. And I find it very strange that a CAN message that would list all of the cell voltages, and that's something only the battery knows, would be eliminated. Certainly they have diagnostics and so forth that might need that data. And so I'm hoping that in failing to send that CAN message, that explains the presence of the 401 message. The other more likely option is that they updated the firmware in the battery and simply don't send it anymore. It's kind of costly in that there's 96 cells and they send 3 cells per message. And so it's quite a bit of CAN traffic to transmit that data. But I'm a little bit hopeful that maybe that's not the case, and that the battery will put that out unless it receives a message saying, we don't need you. We don't need that data. And that's a possibility too. There's a lot of things we still have to investigate in the Model 3 battery, but now we have a prototype that we can do that with. Again, we display all the information on the screen previously discussed, and I can press a C now to turn on our 221, and there our contactors come on. This indicates battery contactors energized, and we get our first negative contactor, and that pre-charges your pre-charge resistor, and 8.5 seconds later, because that's what I have in the configuration screen, the positive contactor closes. And now we can see on our 5-digit voltmeter 357 0.59 volts. And it's reporting a voltage of 357.24. Close enough for government work. I like the meter better, knowing what I do of microcontrollers, but it's still pretty close. And so we're back to, this is on Wi-Fi. It's getting the date and time from our through our internet gateway and our EVTV Wi-Fi here. It's sending UDP messages over to our display, and here we can see 357.2 volts, which is pretty close. 156 degrees centigrade, probably not what we're after here. I don't think I ever hooked up that data thing. Showing 45%. Here's our cell voltages. Now I do have those. It shows up as 16 modules. There's really 4, but it is the correct 96 cells, and we can see what all of them are. Our average cell. Low cell isn't right. I got some work to do there. High cell is, and average cell. And here's, it shows the cell voltage, or if I go to state of charge and back, it shows state of charge. Of course, we don't have any current or power because we're not drawing anything into or out of the battery at the moment. At 45%, we'll have to work some of that out. But if you recall, the Tesla Model S battery module also will run a TCCH charger. So we can take one of our 6.6 kilowatt chargers and hook it up to those 2 output cables and hook the can up to our RJ45 and control a high voltage charger to charge our Model 3 battery. It's likely we have a charge cable and port here. We could probably scrape up a charge port computer and hook it up and get it to charge from a Tesla charging station. But I don't really have any reason to do that. Once we're out through the controller, I can just hook up our regular 6.6 kilowatt charger and control that somewhat more ably than I can the internal charger, and set what voltage I want it to charge to and so forth. And I like having control of those sort of things. So we do, as you can see on the meter, our 13.3 volts is now up to 13.5. My fear there is that it'll charge that battery to 15 volts. That's what I see in the Model 3 for the 12 volt system most of the time. And I think that's pretty capable DC to DC converter in the power control system. So that's why this battery, now I can really shut this off now. And in fact, my voltage went up to 14 right there. Oops, I just shut off. I don't know why that was exactly. I'll turn it back on. Yeah, it needs the 12 volts. I'm not sure why that is, Danu. You should be able to run on the 12 volts off of the thing and not need the battery. So we have some 12 volt issues we have to work out remaining, but we're getting data from the battery. We're controlling the contactors internally. I can toggle that. There, you hear it go off. Lose our voltage. And our C character and they come right back on. And although we do have a pre-charge on the contactors in this box. Now the contactors in the battery, wouldn't it be nice if that was enough? But it does its own pre-charge, and we have no control over it. It's designed for the inverter on the Tesla Model 3 drive unit. We're going to use solar inverters, some with much larger capacitors and so forth. So we have to be able to have our own pre-charge, and so our own external contactors. And this has been the case since our first investigation of the Model S full pack and the Model S modules, and remains the heart of our controller, is really letting you set the limits and controlling access to the battery through our contactors. So the trick was to get the Model 3 to turn in its internal contactors, so we have the 357 volts up to 400 volts input to our controller, and then we control that with some Gigavac, very nice Gigavac large contactors, and a pre-charge resistor, and of course our controller, and which does Wi-Fi, and that's everything derives from that. So we've managed to leverage the last year and a half of work on the Model S batteries into a very slightly different controller hardware-wise, with some different connectors for the control for the Tesla Model 3. And we're successfully controlling the action of the internal contactors and the 12-volt DC to DC converter using a single CAN message. And again, I can toggle that at will as I need to. And there it comes back on. Good job, guys. Nice looking box. Kind of familiar looking. That's what they build 10 or 12 of a week for the Model S battery modules. And now this is our first prototype for the Model 3 battery, and we will continue to working on the software for that and some of the hardware issues that remain. I guess for some time we're probably not going to market a Model 3 controller standalone. We will procure Model 3 batteries and test them and make sure they work here with our controller, and probably sell that as a package. And we may even take that further to combine it with a high voltage inverter, probably from Sandy, to do a power pack. A lot of you have been waiting for this. I get a lot of email messages. We're having some issues with the connectors and some of the hardware here, and and Tesla is in a continuous state of upgrade and enhancement. And so on both their software side and their hardware side, it's kind of hard to keep up with all the changes. It's not like they have the 67 Camaro and then they have the 68. They change things every month. And so I'm not sure there is any such thing as a standard Model 3 battery. And now we have your short range, mid range, and long range versions as well. And so Tesla, of course, is curiously unsympathetic to our cause. They're offering different models of the car and enhancing it all the time. And of course, I approve all that, but the Tesla Model S modules are quite stable, and so we can do a lot of things because we know what a Tesla Model S module looks like and works like, and what connectors it uses. And it's a pretty static situation. The Model 3, certainly on the full pack, is not really precisely that way. We don't even know for sure what CAN messages we're going to get out of what battery. And so it kind of makes it a moving target. Brandon Hollinger bought a couple of the Tesla full pack Model S things, and he keeps asking me questions like, will it work on a Model X manufactured after July of 2019? You know, Brandon, I haven't tested it. It probably should, but I have no idea. Now, the standard thing in American commerce is you tell them, yeah, of course it will. Well, if you ask me what color a house is, I'll tell you what color it looks like it's painted on this side. But I'm not too sure about the other side. And that's served me well in the past. If you want a blanket assurance or a guarantee of anything done at EVTV, we're probably not able to provide it. And things change, and a lot of things change. And I'm the last guy left on the internet who actually is in a position that I might not know the answer. I know all the rest of you are pretty sure you're right, but I could still be wrong. And so there you have it. Tesla's at $547 today. So they can make their damn battery do anything they want to, and we'll just follow along. As long as the stock price keeps rising, I'm pretty happy with it. But we've had kind of a breakthrough this week. We've gotten to the prototype stage, at least, on a controller, and we continue to investigate the Model 3 battery. We're going to hook it up to a charger, and we're going to hook it up to an inverter, and we're going to see if we can make it make power and take power. And but at this point, I think it's a pretty good bet that it will. We'll see. Stay with us, and there'll be more EVTV and Model 3 battery coming at you.